Hello, everyone. So this is our last technical session for Sensys. And so the topic here, what we're discussing here is about light-based sensing and communication. So the first presenting author is Sriram. Is a PhD candidate at National University of Singapore. Is interested in discovering novel user cases for everyday sensing devices. His current research focuses on active sensing systems such as LiDARs and time-of-flight sensors, and the security and privacy implications. So, Sriram, you can go.
Great. Just 1 second. Okay, looks good.
Yeah, go ahead, please.
All right, thank you. Just move one last thing. All right, so hello everyone. I'm Sriram from the National University of Singapore. It's been a long flight, but I'm happy to be here and thank you for coming as well. And on behalf of my co-authors, I'm presenting our work called LAPD, Hidden Spy Camera Detection using Smartphone Time-of-Flight Sensors.
Oh, sorry.
Yes.
Now it's working. Sorry, there was a bit delay. I just see the slides coming up on the YouTube. So go ahead, sorry.
Oh, I think YouTube might have a bit of a lag, but it should be fine.
Yeah.
All right, thank you. Okay, so imagine that I show you a few everyday objects. So a water bottle, a smartwatch, and a Wi-Fi router. So what if I told you that each one of them is hiding a tiny spy camera? Can you find them? If you haven't already, try now. I'll give you a few seconds. Okay, for time that should be enough. So let's see how you did. The water bottle has a tiny spy camera inside the label. The smartwatch has one hidden under the screen. And even if I told you that the router has a hidden camera, can you possibly guess that it's inside that hole? Probably not. I guess you can start to see the complexity of this problem. And what makes this worse is that, well, both the water bottle and the smartwatch can be purchased online for less than $30. In fact, the water bottle is only $15. And if you're still cheap like me, I'm super cheap, right? Actually, we built the Wi-Fi router with the camera by just installing a $1 hidden camera module, and that was it. So this is pretty scary. And this also makes hidden cameras a worldwide problem. And what we see is that there are news articles in South Korea, in China, in US, and in India. It doesn't really matter because wherever you look, it seems that there are hidden cameras everywhere. So we can make two observations now. One is that it's really easy to covertly hide a hidden camera in an object of your choice. And secondly, that in any real world environment with maybe hundreds of objects, they're extremely difficult to find. So there is a power imbalance here fundamentally that favors the attacker and puts us, basically the public, at risk. We are essentially on the back foot. So we can say that hidden cameras are basically not only a dangerous threat, but also an asymmetric one as well. So how do we fight back? Fundamentally, one option we have is purchasing a hidden camera detector. It looks like this. So it has a viewfinder you can look through, and it also has some red LEDs at the back that illuminate the scene. Now, here's an example of the South Korean police trying to use this hidden camera detector to find cameras. You can kind of already see, firstly, that this is a manual process, and also from the poor men squatting on the ground, extremely laborious. Right? This is not fun, as you can see. So what exactly are these people seeing through the detector? Now, imagine you see something like this with your naked eye. If you're in person, you can see the object in front as well. Now, what you'll see through the detector looking at this is something like this. The hidden camera is actually in the top right-hand corner of this plug. But if you look through the hidden camera detector, there's an unnaturally bright reflection where there's supposed to be nothing. Now, that's a really interesting point. And now we should really ask ourselves, well, what makes hidden cameras reflect so brightly compared to the surroundings? We can take an example here of two objects, one without a hidden camera and one with. If we shine incoming light at both of these objects, the object without the hidden camera does something called diffuse reflection, or basically weakly reflecting in all directions. And the object with the hidden camera reflects the light back very strongly in the direction of the source, which is called retroreflection. So looking sort of closer at the hidden camera, we can see this as a combination of an image sensor and a lens that focuses light onto that sensor. So when we shine incoming light, what happens with this geometric configuration of lens and sensor is that all light goes back to the source, almost all light, very strongly. And this is called here lens sensor retroreflection. If this analogy is too abstract, you can think of a concrete example as cat eyes. I'm sure everyone is familiar with cat pics everywhere. If you shine a bright light on a cat's eyes, the geometry of the eyes will shine a lot of the light back to you, and they're much, much brighter than the surroundings. This is the exact effect that happens in hidden cameras as well. So now we should talk about the elephant in the room, in case you haven't seen it yet. The issue here is that there are many, many other reflections that are also bright in the hidden camera detector's view that aren't the hidden camera itself. So more specifically, we can talk about some of these drawbacks, including many, many false positives for this hidden camera detector, and also multiple usability concerns, including the fact that this is a manual process. There is no automation. You have to decide yourself. So this is a lot of subjective judgment. There's also a specialized device that you have to carry with you at all times. You become that one-use hidden camera guy or girl that has that in your pocket, and that is incredibly infeasible to have this one detector with you. And lastly, I'm sure that somebody who tried yesterday can also find that there's a lot of eye strain with this device. If you hold it to your eye for maybe 20, 30 seconds, it gets really tiring as well. So there are multiple issues with this hidden camera detector that we can purchase on the market. So we asked this question, whether we can automatically and accurately locate hidden cameras using only everyday equipment that we have on us at all times. So let me paint a picture. What if I wanted to suspect that something has a hidden camera, I could just take out my smartphone and it would tell me that there's a hidden camera in that region. In fact, this is exactly what we do, called LAPD, or laser assisted photography detection, which is a means to automatically locate hidden cameras using laser time of flight sensors on smartphones. So how this works is that LAPD illuminates the region with this time of flight sensors laser output, and any hidden cameras in the region will return a uniquely bright reflection. We will analyze this reflection and indicate it on the screen. That's the fundamental idea behind LAPD. Now, I've skipped over something, which is, well, what is a smartphone time of flight sensor? Now, the idea behind this is something that's increasingly common in modern smartphones like the Samsung S20 Plus, iPhone 12 Pro, even 13 Pro recently as well. And the point of this sensor is to get depth information, so how far away objects in the scene are. Well, this is really useful for stuff like augmented reality, like games, or even utilities like planning where furniture goes in your house, augmented reality primarily. And the idea here is that we measure distances from the camera to nearby objects using laser travel time, either directly or indirectly. And as an example of how this looks, if you have this image of, let's say, a water bottle, now what a time of flight sensor sees when it looks at this image is something like this, right? Where a darker region in this image refers to something that's closer. So it really is a depth image. The two can be combined to produce something like a three-dimensional image. That is the fundamental conceit of what a time of flight sensor is. So what are our insights? What do we gain from this, looking into time of flight sensors? Now, firstly, something really interesting is that if we look deeper into, the APIs of the sensors, not only do they give you depth information, so how far away things are, they will also tell you how bright each pixel in the image is, how bright the reflection was, right? Now, we'll talk a little bit more how limited that is, but it will give you some information like the image on the right. So what this means is that you can find regions that are unnaturally highly reflective. Specifically here, these are black regions in the image, so connected black pixels. Unfortunately, I think you can tell that this is not a straightforward problem yet, because only one of these reflections refers to a hidden camera. All the other reflections are false positives. And this brings us to some of the numerous challenges that LAPD is facing. So these are some of the challenges that we are facing. Firstly, every object has a varying reflectivity, which causes a number of problems. Secondly, there are multiple hardware limitations with this sort of lousy TOF sensor. I say lousy, of course, in our application, but not in general. And lastly, every hidden camera also has a limited field of view, and we cannot see the camera outside this region. So let's look a little bit more at these challenges. Now, what I mean by varying reflectivity is that, once again, we cannot stand too close or too far from any object we want to scan. Why? So imagine, once again, this water bottle as a reference, and imagine we stand at multiple different distances from this bottle. Now, if we're too close to the bottle, what we see is that the sensor is saturated, too much light returns back to the sensor, and any hidden camera is completely obscured. If you're at the right distance, or what we call the ideal distance from this object, the hidden camera here appears in green as a small region of connected pixels, and it's easily visible at this range. Unfortunately, if we go too far, not enough light comes back to the sensor, and once again, we just don't see the camera. So there are lots of false negatives that come into play if you're not at the right distance from each of these objects. That's our first problem. Now, The second issue is that the time of flight sensors that we have now have extremely limited spatial resolution. What I mean by that is that they have almost a 320 by 240 sort of measly resolution image. This is what we get at all times. A good analogy, of course, if you're not familiar, is that given an image that looks like this, a lower resolution will give you an extremely blurry picture with very few details. This means that a hidden camera actually is only represented by 1 or 2 pixels at the end of the day. So really, really few pixels. Now, this problem is additionally compounded by the fact that every single pixel in this image only has 3 bits representing it, or only 8 colors. Once again, analogously, an image like this will seem like a very sort of lousy grayscale image with very few layers to it. So these two issues compound to create a number of false positives where we need to filter out spurious reflections to find the real hidden camera as well. And lastly, for a challenge, hidden camera reflections, because of some fundamental physics, are only visible within a 20-degree field of view. And basically, if you're outside that field of view, you just will not find the hidden camera. It will not be visible to you. And this is, once again, a fundamental physics limitation. So given these challenges, how do we address them? So that's the point of LAPD system design, where we have 4 phases to identify hidden cameras. So firstly, we select the hidden camera object on the screen. This is a smartphone app. Secondly, the app will guide you through a series of steps to find the ideal distance. Thirdly, the app will guide you through a series of sort of a scan, a scan pattern to look at multiple places in the object. And lastly, you'll be told whether that object has a hidden camera or not, and exactly where it is on that object as well. So let's zoom into the third phase where a lot of the work happens. So each frame from the time of flight sensor gives us a laser intensity image and also a depth image as well. We combine this in one big stage to basically filter out a number of false positives. So imagine, for example, we actually see the hidden camera and a number of false positives. We don't know this yet. The point of this phase is to use both physics-based, so sort of physics knowledge, and also machine learning filters to remove all of the false positives in this step. Then any remaining reflections that pass this stage are passed to a 3D coordinate convergence system. And finally, we pass it through one last filter that checks for the field of view of the camera and whether this makes sense, whether it checks out. And finally, if everything works, we will indicate whether a hidden camera is present or not. This is the overall design of LAPD. So I can only mention 2 of these sort of phases for time, but I'll just quickly go through them. Firstly, how the scan distance computation phase happens. How do we find the right distance to scan from an object? So basically, the intuition here is that any tiny hidden camera, we define these as 1 to 2 millimeters, which is very common. This will only generate reflections that are smaller than, let's say, some p number of pixels. Right? So anything that's larger than this cannot be a hidden camera. There is no way. Right? And this p is basically an empirically determined value based on the resolution of the time of flight sensor and also how large we assume the cameras are. So we have this sort of threshold p. Now, what we do then is we ask every user to stand within 20 centimeters of the object to saturate the whole sensor, and we ask them to slowly move backwards. What happens over time is that you get to a point where all reflections in the scene are smaller, or at least as small as a hidden camera can be, and that's considered the ideal distance. So for those of you who like graphs, of course, the idea is that the further you get away from the object, the smaller the largest reflection becomes, and at some point it's lower than the threshold that we know for a hidden camera, and that becomes the ideal distance. So that's how we figure out where to stand for each object. Now, second phase we'll go through is how we remove a vast number of false positives, because there are many. There can be hundreds per frame. So how do we do that? So once again, we take the laser intensity image. This is the baseline here. And we extract all of the high intensity regions, so connected black pixels. And what we do now is that we feed this to a series of shape and distance filters, as we call them. So I'm going to present only a subset, but one of them, for example, is whether the reflection is too large. Another also uses the knowledge that all lenses are essentially circular because of manufacturing reasons on a lathe. So it tends to be that any reflection is circular. So anything that's square or rectangular cannot be a hidden camera as well, and that's also removed. So the number of other things we do here as well, but basically all of the difficult cases, the really difficult ones, are passed to a deep learning filter. And this is trained over our own self-collected data set, but this is basically a convolutional neural network that runs in real time to remove a vast number of false positives as well, integrating multimodal information from both depth and intensity. And finally, this outputs the reflections that are candidate hidden cameras, and everything else is removed. Now, of course, here I'm really simplifying because there's a lot of information that we fuse across frames and across 3D space, but you can refer to our full paper for more details. So now that we know how LAPD works, let's talk about how we evaluated its performance. So LAPD's hidden camera detection performance is tested against 30 different objects that LAPD has not been trained on before. I repeat again, we have not trained on any of these objects. 21 of these test objects do not contain hidden cameras, and 9 of them do. So across both of these classes also, we were a little bit mean to ourselves. We basically had a bunch of objects that were highly similar across both classes to make our task even more difficult. And here again, like I mentioned, we have a totally separate training set of 10 objects that we designed ourselves as well, and also things that we bought off the shelf. So for each object, we have a total of 3 detection methods that we're testing, both LAPD itself on a Samsung S20 Plus, but also 2 baselines. One is a hidden camera detector, and the other one is just using the naked eye. So LAPD is tested fully end-to-end as an Android app. So we really did run these experiments on a real environment. But for COVID reasons, we test the other 2 methods using Amazon Mechanical Turk. So we record a bunch of videos that are very fair to the participants, and their job is basically to observe them and annotate on an image where the hidden cameras are. We explain in the paper how we make this as fair and in fact biased towards the participants as well. Okay, so we now summarize the results of LAPD's comprehensive evaluation. So LAPD has the highest hidden camera detection rate at 89%, and also the lowest false positive rate of 17%. Also, it accurately determines the correct scan distance for all 30 objects we tested on. That's never seen before. And also it generalizes across multiple lighting conditions and also the different smartphones that we tested. We tested 3 different smartphones. And lastly, it also can operate continually for 2.5 hours on a Samsung S20 Plus, even regarding the fact that it's running augmented reality, machine learning in real time, and all these other things. And also the QF sensor is running continuously. And this is still true. So in the interest of time, again, we'll only present the first result, the main idea. And let's talk about that now. So once again, the main result from our experiments is that LAPD is outperforming both of the baselines in terms of how many hidden cameras it detects and how few false positives it generates. So recall again that we test this on 30 different objects. And the results are here in this graph, where green bars refer to hidden camera detection rates, and the red bars are false positive rates. So on the x-axis, on the y-axis, we have the percentage of each metric. And on the x-axis, we have on the leftmost LAPD itself, 88.9% hidden camera detection rate and 16.7% false positive rate. And then we have the detector itself in 2 of its modes, which once again, for both of its modes, blinking and continuous LED performs worse. And finally, for just using a naked eye, it performs worst of all. So we outperform all of these methods with LAPD. So given this performance, now we can consider how else we can deploy and extend LAPD in the future. The first thing and the most important thing is that hotels are a massive hotspot for hidden cameras. Now, what we can do instead of manually inspecting everything is that we could just put time-of-flight sensors on cleaning robots, which are becoming increasingly more common in hotels. And these could just automatically scan for hidden cameras through their daily cleaning routine. The other thing we could do is we could also use the smartphone's flashlight as an additional modality to find hidden cameras. And we know this will be really effective because we tried it ourselves a little bit manually, but unfortunately, because of API limitations, we can't do this right now. But if we can do this, and when we can do this, this will be incredibly effective. Lastly, let's talk about a couple of limitations for LAPD. Now, firstly, of course, it's clear that that QF sensors are not completely ubiquitous yet. So they're on higher end smartphones for now, but they're also penetrating into the space into mid-range smartphones over time. So we expect that this will be better over time. Secondly, also, we use a lot of augmented reality libraries that are external to LAPD for localization. And while this is something we rely on, we expect also this accuracy will improve over time since there's lots of active research in this space. And lastly, LAPD right now requires you to select each object one by one to scan them because the sensor is not that great, so it doesn't have much dynamic range. So we expect this to once again get better as we have better and better sensors with larger and larger bits per pixel and so on and so forth. So we expect this once again to get better with time. What we have right now for LAPD is kind of where we are right now with a proof of concept time-of-flight sensor on commodity smartphones. So in conclusion, LAPD is a system that uses time-of-flight sensors on smartphones to automatically find hidden cameras. And our hope is basically for the Sensys community as a whole is maybe we can look at more interesting uses of commodity time-of-flight sensors. Maybe we can find other similar or completely different use cases that can use time-of-flight sensors in novel means. All right, so thank you very much. You can find a full paper here and any questions. Thank you.
Yeah, thank you, Sriram. It's a very exciting presentation. So I will let you take care of the on-site question first.
Thanks for your presentation. It's really a nice work. And here I want to, I only have one concern. That's how do we consider the ambient light interference issue? In here, you take a bottle as an example, but in reality, maybe it's the spy camera will maybe fixed at other places like the wall and the ceiling, and these places are near to the strong light source like the TV or a ceiling light. So how do you consider to cancel this ambient light interference? Yeah.
Yes, that's an excellent question about like, so you're talking.
Yeah.
You're talking about external light sources, like, for example, like ceiling lights or the TV
or
itself.
TV light.
Right. The good news is that time-of-flight sensors operate in a very narrow frequency range. They're only at 850 nanometers. So any light source that firstly isn't within 850 nanometers just isn't going to matter. The second thing is that they're even more robust than we expect. So even if you take two smartphones, both with time-of-flight sensors, and you put them back to back and you shine them in each other, they actually don't interfere between themselves. So in fact, this is a really robust system of detecting laser light that is almost key to the smartphone itself. So generally speaking, when we tested this as well, background lighting is not a concern. We tested in sunlight, in bright indoor lighting as well as dim lighting, and there's almost no difference at all between all these situations. So we don't expect background light to be a problem. But yes, thank you for your question.
Thanks. Got it.
Well, is that no on-site question anymore? So if no on-site question, I look at the YouTube and both YouTube and Slack. I'll get one. So Yuan Qingzheng from Hong Kong, he is asking, how long does it take for an ordinary user to completely check a hotel room? That's the first question. And second is, did you test with volunteers with their naked eyes in real world scenarios?
Thank you. Great question. Sorry, two questions. One about how long it takes to scan a room, and the other one about volunteers. Okay.
Right.
So when it comes to scanning, basically scanning room, depending on the number of objects that are there, will take some time. Of course, per object, we expect that to take about 30 seconds to scan. So each object will take about 30 seconds to scan. So you need to look at how many objects there are in the room because you're selecting object by object. But I do want to stress the fact that this should be compared to the current state of the art, which is this hidden camera detector that I'm holding. This is also the same idea where you turn it on and you manually sort of go object by object as well. So in general, it will take about 30 seconds per object. And I guess for a room, maybe you can estimate that to take something like maybe 5-10 minutes. Yes. So that's the first question. For the second one, do we use volunteers to test the naked eye and the detector? So while they weren't in the room physically using the detector and naked eye, because of COVID reasons, we couldn't get all the participants on site. What we did was that we basically recorded a series of videos where we did these scans ourselves very fairly as well. In fact, the paper states that for all of the hidden camera usages, we actually ensure that at least the reflection from the hidden camera is visible in the video. We put all those videos on basically Amazon Mechanical Turk, and basically all these participants sort of looked at these videos and then decided where on the image the hidden camera was. So they weren't there physically in the room. We basically, as a proxy, we recorded a large number of videos very fairly as well, and we asked them to annotate where the hidden cameras were. So I hope that answers both of those questions.
Right. So I actually got one question from myself.
Yes.
So suppose I'm a hacker. So does it make sense that I just hide my camera behind a mirror? Would that thwart your mechanism?
Right. That's a really interesting question. Actually, so this actually comes out quite often about mirrors and one-way mirrors. So generally, if you have a mirror, what happens is that actually, let me answer your question quickly first. So if it's behind a mirror, should we be able to detect it? I think we will still be able to detect it for a couple of reasons. Firstly is that you still need to expose the lens of the hidden camera. So somehow you have to find a way to insert it into a mirror that still exposes the lens without somehow breaking the glass. But in general, even if you did that, a mirror generally has a very large reflections that are easily filtered out. So the actual hidden camera reflection is generally visible as well. So I don't think mirrors would necessarily pose a direct challenge. But also we didn't test this explicitly, so we don't know for sure, but we did test against multiple kinds of reflected objects. Yes. So
okay, thanks. We got some more questions from YouTube, but maybe because of the time limit, I'll just put them into Slack and let you do it offline. How about that?
Sure, no problem.
Okay.
All right, thank you everyone. Thank you for listening.
Thank you. So let's switch to the second presenter. When Zhiyuan is putting on his slides, let me just introduce him. Xie is currently a PhD candidate in the Department of Information Engineering, the Chinese University of Hong Kong.